In this tutorial, we will solve Laplace equation using an iterative method called Gauss-Seidel, and we have seen this method before. If you go to page 301 in your book, there's an example that shows you how this set of three simultaneous equations is solved with some initial value assumed, and then initially it's set to 0 for each value, but that every time it solves one equation, it uses that value in the next equation to solve for the next value, and it repeats this process until a certain desired error is achieved. So we will use this approach to solve our Laplace equation for the temperature field, and we can rewrite our equation in the form of Tij is equal to the average value of the neighboring four points. So in this case, I think this -4 is a typo, but these four temperatures, neighboring temperatures added together divided by 4. So let's try to implement this. Here I have same problem that we had earlier. So let's create a blank temperature field. And again, I've set up the boundary values already because we know what these temperatures are, and we need to fill these gaps. Now let's initialize the middle part with zeros. So now we have zeros in the middle part, but we want to adjust these values using Gauss-Seidel. But I know that this value should be an average of these neighboring values. So I will adjust this value to be, so in this case, as you can see, it'll be 0 plus 50 plus 0 plus 0 divided by 4. So this value will become 12.5 in the first iteration. Then when I go to this value, this will be 12.5, which I have already calculated, plus 0 plus 0 plus 0 divided by 4, which will be roughly I believe 3.6. And we keep repeating that process until there is no longer change between, or the iteration error reduces. So here is the first iteration. I'm going from in x direction, I'm going from 2 to 4. In y direction, I'm going from 2 to 4. So these are the 9 values that will be filled. And let's say I set x is equal to 2 and y is equal to 2. And based on that, I find t. So if you see, as I suspect, as I told earlier, this value has been replaced by 12.5. Now let's say we go to the next value, which will be y is equal to 3, and rerun this code. So that actually 3.125. And so we keep repeating that. So what I'm going to do is I'm going to clear reinitialize it, because I'm going to be running the whole loop. So let's run the whole loop and see what happens. So that's what the values are, and if I plot it as a mesh plot, you can see the boundary values are fixed, but these values have a little bit shape to them, but not very clear. So let's rerun the for loop, and again type the mesh command. So you see it came up a little bit, and you can always say, well, I want to see the previous value. I want to save the previous value. So you can say t p is equal to t, and then when I get here, I will always be able to look at the difference between the two. So let's say that's my tp, and now I rerun this code, and so I have tp, which was the previous iteration, and t as a new iteration. I can take the difference and see how these values are, and I can add these values or take the the sum of squares of these values to see what the error is. So I can define error as t minus tp, and then I can take the sum of the squares of these errors. So I can sum or I can take the average, so mean error, which will be error from 2 to n minus 1 and 2 to n minus 1 whole squared, and I'm taking the mean, and I'll have to apply a mean twice. squared, and then I have to apply mean. Actually, let's just apply mean twice, and this will give me the average error. So let's run this. Let's define E, and then let's run this. So this is my average error, 79 point. So let's run this again, and let's see if this error reduces. So it's gone to 27, and again 8. So as you can see, it keeps reducing, and if I look at my mesh of T, it also keeps coming to the closer value. So now with that done, let's write an iteration loop. So for k is equal to 1 to 10, let's say I want to run it 10 times, and then I want to keep track of my previous value, and I also want to find the error between current and the previous value, and then I want to display. I want to create the mesh of T, and then I also want to display the error, and then I want it to pause until I press the next key. So here is the error of 885, and as we see, the error is reducing and the plot is getting closer and closer. So you can always set a condition here that if E is less than, let's say your tolerance is 1 into 10 to the power minus say 4 or 3, even 3, which is pretty reasonable, then break from this loop and end. Now you can even put a bigger iteration here, but it will stop when that condition is satisfied. So it stopped at the earlier condition. So actually we should see at what iteration it stopped. So we'll put K as well as E. Okay. So now you can see how this works. Now the advantage of this method is that we can increase the number of the nodes. So let's say n is the number of nodes, and we want to do it for say 25 nodes. Now I can create a matrix which is 25 by 25, and then the only change I have to make here is possibly actually I don't have to, the loop. So the loop will go from 2 to n minus 1 and 2 to n minus 1. Other than that, everything should work just fine. So here's the first iteration, error 92, and as I keep moving forward, as you can see, the error is reducing. Yeah, as you keep pressing enter, the iterations are increasing. So it looks like by 100th iteration it may be done or may not be done. So it looks like it didn't. Now I'm going to remove this pause, actually change this pause to maybe 0.01, so I don't have to press enter key, and change it to 1000. And now let's run this. So it looks like on 193rd iteration we got the needed tolerance, and this is the profile of the temperature for the given problem.